have a quick recap, we are studying wave optics. We have started with Huygen's theory. Then we have seen the reflection through wave theory of light. Then we have seen wave fronts. What are wave fronts? Then we have seen the big huge chunk which is interference. Then we have started with part of diffraction in last lecture. Just to have a quick refresher, what diffraction basically means. Diffraction means bending of a light or light waves, to be precise, around the edges of any obstacle or any object. It may be a slit, it may be the actual object, it may be a grating, it can be anything. That is what we call it as a diffraction. So based on the concept of diffraction, we have two types of diffraction. To be precise, it is dependent on the experimental setup, the distances which are involved in the experimental setup. We have a Fraunhofer diffraction and another was a Fresnel diffraction. We had a quick glance about Fraunhofer diffraction and Fresnel diffraction in yesterday's lecture, and we have started with the understanding of experimental setup for Fraunhofer diffraction. We had the understanding, we had a knowledge of understanding about these type of diffractions, and we have started analyzing this particular diffraction pattern, specifically focusing on the location of minima and maxima. That is a part which we have started in yesterday's lecture. So what happens in this particular diffraction for that matter? You have lots and lots of different things which we need to focus on. This AB is a slit which we have considered, where O, it stands for the midpoint of this particular slit. Now, what is the width of the slit? It is given by this A. What is the distance between the slit and the screen? It is given by D, which is considered to be approximately equal to the focal length of the lens, this convex lens which is used. Now, giving us the two different paths, one is AB path which goes in this straight line, forming one point P0 or P0. Another path which goes along AC at a certain angle theta. Why? Because bending around the edges, around this edge for that matter, giving us the another point P on that particular screen. So we were understanding the locations of minima and maxima. So what do we get? Just like before, we have already seen this slide. Again, let's go into details of that. We have two sets of parallel rays. One goes along the slit AB and one is slightly at an angle theta. Both of them intersect at P0 and P respectively. So the central beam which we have, which is the central point we consider P0 or P0, which is directly in front of O and acts as a center of the slit. So you can see there is a straight line. It is exactly in front of the center of that slit. So what we get at P0 is the constructive interference, where the point P is formed. It is at an angle theta. So due to the edges at point A, diffraction of light it takes place. Means what? A ray of light at this edge bends through this angle theta. Due to that, we get another set of rays at an angle theta which intersects at point P. So when we consider this AC, how that angle theta is there, basically that this AC is perpendicular to this line AM. So this angle is 90 degree. That is how this diffraction it takes place. Now what this basically represents, that there is no path difference or phase difference between these rays. There is no path difference means what? Both of them they reach at same time. No phase difference. Again they reach at same time. Okay. So this is the part which we have covered in the last lecture. In case of next, moving forward with this particular point itself, again we have to take help of this. Since there is no path difference or phase difference, we can consider path difference between AB and AC will be equal to BC. BC क्या है? ये BC है. So between AB and AC पाथ डिफरेंस कितना होगा? ये BC इतना होगा. सिंपल. क्यों? क्योंकि यहाँ पे तो कुछ प्रॉब्लम है नहीं एट पॉइंट A, बट एट पॉइंट B, B से कहाँ पे जा रहा है? C पे जा रहा है. So at this BC and BC को we can write it as A into sin theta. कैसे? सिंपल है. sin theta क्या होगा? अपोजिट अपॉन हाइपोटेनस. अभी ये 90 डिग्री होगा ऑब्वियसली. So sin theta will be opposite, मतलब BC into hypotenuse मतलब A. So sin theta is BC upon A. So BC will be A sin theta, which is equal to the lambda. Lambda मतलब क्या? Wavelength of that particular light. Now we assume, let's assume a point K. K is the midpoint of AC. ये point है K. यहाँ पे देखो. जैसा AB का मिड पॉइंट O है, वैसे ही AC का मिड पॉइंट वी कंसीडर एज K. So what we can write? We can write OK. Okay, this distance will be half of BC. Basic geometry in any particular triangle. Line joining two midpoints. ये theorem तुम लोग 9th standard में किया होगा शायद. So OK, this line is half of that of BC. Means what? OK कितना होगा? Lambda by 2. Why? Because BC is lambda. So what is the path difference between AP and OP? So path difference between AP and OP will be lambda by 2. कैसे? BC कितना है? लैम्बडा है. OP कितना होगा? मतलब ये OK कितना होगा? लैम्बडा बाई 2 होगा. और ये कितना है? 0 है. तो 0 एंड ये है लैम्बडा बाई 2. मतलब डिफरेंस कितना हुआ? लैम्बडा बाई 2. That is the path difference which we have. So based on this, we can say that at point P, destructive interference has formed. Okay, why? Because the path difference at point P is lambda by 2. So since the path difference is lambda by 2 at point P, interference which is formed as destructive interference. Okay. Now we are going to consider two more points. Okay. Which two more points? We are going to consider points G and H. This is point G which we have over here, and point H which is over here, which are equidistant from A and O. मतलब क्या? The distance between A and O, मतलब G is the midpoint of AO and H is the midpoint of OB. Okay. Now AO का distance कितना होगा? Half of that, A by 2, and OB का distance will be half of that, which is again A by 2. So when we consider from a rays when they start from G and H. So if we consider the point PD, we can consider it as again lambda by 2. So at point P, what we get? We get a destructive interference. Means what? We have it as a first minima. So this is the point where the first minimum is possible, a destructive interference, right? Any doubts till this point? Bolo? Yes or no? Okay, Prathamesh is asking me about path difference. देख path difference मतलब क्या? Difference in path. ठीक है? So when we consider at point A, यहाँ पे तो कुछ difference है ही नहीं. But B से क्या हो रहा है? वो C पे जा रहा है. तो वो कितना होगा? लैम्बडा होगा. तो AB और AC में डिफरेंस कितना है? AB और AC में डिस्टेंस है ये पाथ में BC. तो वो है लैम्बडा. अगर हम लोगों ने पॉइंट K कंसीडर किया तो O से डिस्टेंस कितना होता है? लैम्बडा बाई 2. मतलब AP, ठीक है. सो A जब P पे पहुंचता है और O जब P पे पहुंचता है, व्हाट इज द डिफरेंस बिटवीन देयर पाथ्स? टोटल पाथ विच इज अंडरटेकन, इट इज लैम्बडा बाई 2. मतलब क्या है? वहां पे डिस्ट्रक्टिव इंटरफेरेंस फॉर्म हो रहा है. लैम्बडा बाई 2 का मतलब क्या होता है? अज्यूम करो व्हेन यहाँ पे क्रेस्ट हो तो दूसरे का ट्रफ आता है, इसलिए हम लोगों का इंटेंसिटी जीरो मिलता है. दैट इज व्हाट द पाथ डिफरेंस इज ऑल अबाउट. अभी G और H के केस में क्या हो रहा है? G और H के केस में भी what is happening when the ray goes from G to P and H to P, path difference वापस कितना आ रहा है? PD बोले तो पाथ डिफरेंस कितना आ रहा है वापस? लैम्बडा बाई 2 ही आ रहा है. मतलब यहाँ पे क्या हो रहा है? डिस्ट्रक्टिव इंटरफेरेंस फॉर्म हो रहा है, which we call it as first minima. ओके, समझा प्रथमेश? Okay, so this is what we have established now. At point P0, what we had a constructive interference, and at point P, we have destructive interference. So now moving forward with this particular point, this is for path difference lambda by 2. So if we go on considering the multiples of it, if we have for path difference multiple path differences, maybe 2 lambda, 3 lambda, 4 lambda, so on and so forth, n lambda, multiples of lambda, what we will have? All the points, they will be dark. Means what? We will get the destructive interference over there. So this is applicable for point which is at P naught as well. वो भी हम लोग देखने वाले बाद में. So at points P, what we get? We get dark fringes, destructive interference, and point P0, what we get? At point P0, we get bright fringes. So when we consider the consecutives of them, what will happen? Same condition can be used for consecutive points afterwards, right? So here at point P, कितना था? यहाँ पे लैम्बडा था, तो हम लोगों को डार्क फ्रिंज मिला. तो उसके बाद कहाँ पे मिलेगा? 2 लैम्बडा पे मिलेगा. उसके बाद कहाँ पे मिलेगा? 3 लैम्बडा पे मिलेगा. So on and so forth. At n lambda, we will get a dark fringe. So for nth maxima and nth minima, we can write the conditions like this. So if we consider nth minima, minima कहाँ पे होगा? A sin theta, which is equal to plus minus n lambda. And similarly, nth maxima, the path difference can be given as A sin theta, which is equal to plus minus n plus half into lambda. So what we get in simple words, we get one maxima between two minima. Or we can say other way around as well, we get one minima between two consecutive maxima. In simple words, what do we get ultimately? We get the diffraction pattern of alternate dark and bright fringes, or maybe dark and bright circles for that matter, whatever we can use. Clear? Any doubts till this point? Bolo re, yes or no? Good. So once again, these two formulae, the first one and यहाँ पे one है, I forgot to give two, I think यहाँ पे दिया नहीं क्या मैंने second one, हाँ नहीं दिया. So this first one and the second one, these two are the conditions for nth minima and nth maxima. Minima मतलब क्या? Once again, constructive interference means you get, sorry, minima मतलब destructive interference means you get a dark point. Maxima means constructive interference means you get a bright point. That's it. So these two are the equations for dark and bright points, dark and bright fringes, dark and bright circles, whatever you call. Now we are going to use these equations next to find out what we have as the distances of minima and maxima from central bright point. Okay, means what in simple words, distances on the screen. That's it. Okay, ये याद रखो, central bright point इसको हम लोग बोलते हैं CBP. Okay, just shortcut में, बाकी कुछ नहीं. Now, using equations 1 and 2, we can write path difference at locations of nth dark and nth bright point. We can write just a moment. So equations 1 and 2, what basically it gives us? It gives us the path difference at locations of nth dark and nth bright point. Right? Now what do we know? We know that distance, this distance between the slit and the screen is very, very, very big than that of distance between the two slits. At the same time, we know that the bending which is taking place is comparatively very small. So for this particular concept, for this particular application, if we are to consider it in radian, again we know that sine theta is approximately equal to theta, or tan theta is approximately equal to theta, which we can consider as y upon d. अभी ये y कौन है exactly? Y is the distance of point P from CBP. CBP मतलब क्या है? यहाँ पे ये अपना point है, ये CBP है, central bright point. This is the point P which we have on this screen. And इन दोनों में जो distance है, this distance is what we are considering as y. So again, basic geometry, we can consider sine theta or tan theta, which is equal to theta, which is equal to y upon d. And d to khair, you already are familiar. D is distance between the slits and screen. This is what you already are familiar with. Okay. Now, using this particular concept, we are going to move forward. Okay. So, in this particular case, we are going to assume certain points. Okay. Let yn, focus on d, yn d, we are going to consider distance of nth dark point from CBP, and ynb as the distance of nth bright point from CBP. Once again, what is CBP? CBP is the central bright point. nth dark है इसलिए nd आया, nth bright है that's why nb आया. So at nth dark point on either side of the CBP, we have already seen that diffraction pattern is alternate dark and bright bands or alternate dark and bright fringes. So it can be used that sine theta is equal to n lambda. Okay. So at any dark point on either side, we can use this particular. This is the condition which we have for nth mean. This is one CBP point. So using this particular condition, we know that sin theta is approximately equal to theta. So we can theta nd. This is for dark, which is y nd upon d. ये हम लोगों ने last time देखा previous slide पे. But theta can be equal to n lambda upon a as well. ये sin theta को हम लोग लिख सकते हैं theta. So theta can be written as n lambda upon a as well. So what we will get, which is also equal to n lambda upon a. So we will get in terms of y n d can be as n into lambda d upon a, which is equal to nw. और w क्या है? W is lambda d upon a. We're going to go into details of W in a minute, but for the time being, is there any doubt? Or a yes or no? Okay, good. So once again, this formula is very, very, very important. Once again, what is YND? YND is the distance between the nth dark point from central bright point. वो कैसे find out करना है? Using this formula, you can find that distance out. Okay, maybe first bright, first dark, second dark, third dark, 10th dark, wherein value of n will be 10, so on and so forth. We can find the distance of nth dark point from central bright point. Now this is what we have done for the dark point. Similarly, we can do this for the bright point as well. So for nth bright point, once again on either side of the central bright point, CBP, equation which we are going to use, a sin theta is equal to plus minus n plus half into lambda. So यहाँ पे भी instead of sin theta, we can directly substitute for small angles. Obviously, we can directly substitute theta. So a, it goes over here. So it will be lambda upon a. Theta is equal to, once again from previous formula for bright, we can write theta nb is approximately equal to ynb upon d, which again is approximately equal to n plus 1 by 2 into lambda upon a. So once again rearranging the terms, this d, when it goes to RHS, it will go to numerator. So what we will get? YNB, notice the letter B. B stands for bright. For YNB, we will get n plus half lambda d upon a. Or we can write it as half into W, where W is lambda a. Now what exactly is W? W is in the consecutive fringes, except the central bright fringe, P or C or zeroth fringe, as we can call it. Okay, so once Y is the distance between a certain point, maybe dark or maybe bright, depending on which point we are considering, from the center. Nth bright point जो बोलते हैं हम लोग, lambda, we have the wavelength of light. Big D, capital D, is the distance between the slit and the screen, and A is the distance of the, or the width of the fringe or the slit itself. Okay, here the slit we have AB, or A is the width of the diffracting element. Clear? Any doubts in this? So we had a formula for YND, which is YN for nth dark, and YNB, which is dark. Any doubts in this? Bolo re yes or no? Good. Now moving on to the next part about diffraction. Again, we have not completed this. This is the last part in Fraunhofer diffraction. We need to find out the width of central bright fringe. We have seen the width of the different fringes, right? But central bright fringe which is formed, uska width kitna hai? That is what we are going to see. Okay. Now, in case of central bright fringe, this generally is spread between the first dark fringes on either side. Means if we are considering at point P, the central bright fringe is formed. So this will be on either side. Matlab yahan pe it will be spread on upward direction at the same time in downward direction as well. Yahan pe screen pe. Right? So when we consider the width of central bright fringe, it is the distance between the centers of first dark fringe on either side. Right? So in simple words, what we can say, central bright fringe का width कैसे निकालेंगे? First dark fringes का center. Okay? मतलब here we are getting a first dark fringe in, let's say, upward direction and first dark fringe in downward direction. तो यहां से लेके यहां तक ये टोटल अगर हम लोग ऐड करेंगे तो हम लोगों को इसका विड्थ मिलेगा. अभी हम लोगों के पास ऑलरेडी फॉर्मूला है. सो WC मींस width of central bright fringe will be what? Y1D, which is first dark fringe. बट अभी 2 times क्यों है? क्योंकि एक ऊपर है एंड एक नीचे है, तो ऊपर का प्लस नीचे का, सो वी विल गेट 2 into y1 plus d. बट वी नो y1 plus d, yd का फॉर्मूला क्या आता है? yd का फॉर्मूला आता है n into w. अब यहाँ पे n कितना है? 1. सो yd will be w और ये 2 ऑलरेडी है, सो इट विल बी 2w. But W क्या है? Lambda D by A. So width of central bright fringe is 2 into lambda D upon A. And once again, this is another very important formula which we need to remember in order to solve our numericals. Okay. Bolo. So with this, we are done with our part of diffraction. Okay, some small points which are remaining that we will cover. But now this completes our analytical part of diffraction. So generally, the obvious question which comes in our mind is, what is the difference between the interference pattern and the diffraction pattern? Okay. We already are familiar with interference pattern, how it looks. We are familiar with how diffraction pattern it looks. Okay, on the first slide itself, I've shown you how the diffraction pattern it looks. If by chance you don't remember that, I'll again show you how the diffraction pattern it generally looks. Okay, Notice the central part which is comparatively bright, and as you go away, the intensity it goes on reducing comparatively. Okay. So now we need to compare between the diffraction and the interference. That is the part which we have over here in our next slide. Okay. To be precise, when we consider the comparison is between not the patterns themselves, but the way in which the pattern has been created. Matlab kya? It is comparison between two experiments. To be precise, Young's double slit experiment, which was carried to find out interference pattern, and the Fraunhofer diffraction, which is the single slit diffraction pattern. So we are going to compare both of them. So let's start with first Young's double slit experiment. Now it has been a long time, but still we will be able to recollect these points which we had over here. First thing, when we consider the slits which were used, as the name itself suggests, it's a double slit experiment. So obviously it will have two slits as opposed to the single slit. This is the obvious difference which we have. But when slits are considered, the slits were thinner than their separation. Means the size of slits were very small than the distance between their slits. That is the first point. Second point, what is used in order to achieve the interference pattern? To achieve the interference pattern, most important point which we need is the coherent sources. And what gives us the coherent sources? We had the two types or two ways to achieve that. Either it will be biprism or Lloyd's mirror. This is what we have seen. Thirdly, when we consider the separation between the slits, means the distance between the slits, we know that the distance between the slits, which was given by small d, was very, very, very small. Practically speaking, it was a few millimeter. This is the part practically as well we have seen it is maybe 1 millimeter or even less than 1 millimeter. As against that, the distance between the slit and the screen was 10 meter. So it was very, very, very small. And how the pattern actually looked like? It was a 30 to 40 equally spaced, stress on equally spaced bright and dark, right? So this was how interference pattern using the Young's double method we got. Now, as opposed to this, let's focus on Fraunhofer diffraction. This is the single slit diffraction pattern which we get. Now, how the single slit diffraction pattern which we get? The single slit diffraction pattern, once obviously it's a single slit as opposed to the double slit. So it is single slit. Usually the length of the slit is approximately 1 millimeter or less than that. Secondly, how the pattern it looks like. Now, as opposed to the interference pattern where we got 30 to 40 or sometimes maybe even more than 40 equally spaced. Here, we got 20 to 30 fringes, means less than that of interference pattern, but now they are not equally spaced. Central fringe, मतलब अपना CBP जो है, central bright point or central bright fringe is the brightest. And that is what we have seen. As we go away from the CBP, the intensity goes on reducing. Here it was equally spaced, मतलब central bright fringe का जितना width है, उतना ही sub fringes का होगा. Whereas here it doesn't happen. We know that the width of CBF or central bright fringe is twice that of all other bright fringes or dark fringes for that matter. Means they are neither equally spaced nor of same size. So this is the part where we compare the interference pattern with the diffraction pattern. So this comparison clearly gives us the idea that obviously interference and diffraction are two separate concepts. Even though they are related, they are totally separate concepts with the separate applications. Clear? All the formulae for interference. This third column, it has all the formulae which are associated with interference, and this is all the formulae which are associated with diffraction for that. Okay, so definitely you can see the difference that this W it stands for fringe width or the bandwidth which we are considering. In interference it was lambda d upon d, here it was lambda d upon d. Now lambda to same hai, d to same hai in both the cases. Here d, which is distance between the two slits, is analogous to the width of one single slit, because here we have a single slit and here we have two slits. It's a double slit. Now why don't we consider the width of each slit, because it is very small, that's why we can neglect it. Okay, now keeping in mind this is the bandwidth for other widths except for CBF, except for central bright fringe. Central bright fringe का कितना 2W होता है. Only for slit fringe is 2 times the fringe width of other fringes. So that whatever all four types you have, this is keeping that this is for a bright fringe. Okay, so phase difference in case of double slit n pi plus half into 2. Have lambda n lambda, यहाँ पे n plus half है. So if you okay, is my voice breaking? हो सकता है ना? Okay, check कर रहे हैं. Hello, hello, hello. Okay, do let me know if it still persists. Okay. Continuing on, once again we will repeat the part. For nth bright fringe, this all analysis or the all formulae we have for nth bright fringe. Notice that if you have n in, especially over here, if you have n in case of interference pattern, you substitute that n with n plus half, you will get formula for diffraction pattern. So again, this is for your benefit. Even if you remember everything from this particular column, simply substitute n with n plus half, except over here. Substitute n with n plus half, you will be able to get all the formulae which are for diffraction pattern. Okay. Now, abhi aa raha hai sound properly? Yes or no? Hello? Are we able to hear? Is it proper? Okay, good. So If you remember this particular part for bright, then you can just add half and you will get bright for diffraction pattern. Similarly, we have for dark fringes as well. So for dark fringes, this is the table we have. Again, similar type of formula for phase difference, angular position, path difference, and distance from the central bright spot. You have the formula for double interference pattern as well. This again I have taken from your textbook. Again, if you notice, you will find some similarity. Now, exactly opposite to that of previous, you have over here. If you consider for diffraction, if you substitute all the n's with n minus half, you will be able to get the formula for interference pattern. Once again, except over here. So this will be easier for you to remember the formula. nth dark का diffraction learn करो, nth bright का interference learn करो. इंटरफेरेंस में ब्राइट में ऐड हाफ करके तुम लोगों को डिफ्रैक्शन का मिलेगा, डार्क में डिफ्रैक्शन को माइनस हाफ करके इंटरफेरेंस का मिलेगा. So in this way you will be able to remember all the formulae without any problem. Okay, now any doubts till this particular point? Bolo re yes or no. Okay, good. Looking at the time, almost 8:30. So once again, today we'll stop over here. And in next lecture, whenever we'll have our next lecture, we'll move forward from this particular point. Okay, a very small part in the diffraction which is remaining, just a couple of slides. After that, we'll move forward with the third biggest topic in this particular chapter, which is resolving power. Okay, so once again, I hope you have understood anything. Please keep on revising.